Back in 1915, Albert Einstein gave the world his new theory of gravity, the general theory of relativity, which is based on the beautiful idea that gravity is nothing but warps and curves in the fabric of space-time. Now, barely a year later, Einstein pushed this idea one vital step further. You see, he realized that if space is flexible enough to warp, then it should also be able to ripple, to vibrate, to undulate. And that would mean that if something were to jostle the fabric of space-time, it should send out ripples in the fabric of space, and it's those ripples that we now call gravitational waves. Now, of course, the source of gravitational waves would not be my hand jostling space. Instead, it would be some highly energetic astrophysical process like rapidly orbiting neutron stars or black holes that would send out a steady rumble of gravitational waves. Or at least, this is what the theory says should happen. Now, how do you test this idea? Well, the math shows that as a gravitational wave rolls by, it will squeeze and stretch anything in its path. You see it happening here for the Earth, but of course, this is highly exaggerated so you can see the effect. When you do the calculation, you find that the amount of squeezing and stretching would be tiny, a mere fraction of an atomic diameter, and that makes it pretty difficult to detect. But that is what the LIGO team has now achieved. And they did it with two detectors, one in Louisiana, the other in Washington State. And in these detectors, what they do is they fire laser beams along two 4-kilometer-long evacuated tunnels. And when the light recombines, it creates an iconic pattern. It's known as an interference pattern. But the only thing that you need to grasp is that were a gravitational wave to roll by, it would squeeze and stretch the arms of the detector, and that would have a measurable impact on that interference pattern, causing it to shift. And it's just that kind of shift in the interference pattern that the LIGO team has now observed.